Any more crews? All right, here we go. So we're gonna start a whole bunch of stuff. Some of it you may know, some of it you won't. Relax. We're gonna try to go as fast and as slow as possible. And I know, what is that called? Like an oxymoron or something? I know going fast and going slow doesn't make any sense because there's no such thing as fast and slow. But trust me, it is. Okay, here we go. An angle in standard position and Cartesian coordinate system so we're talking about angles here. So if I have a coordinate like this, an x and y axis or x and y grid, the way you measure an angle, you always start at the origin. And it says here its initial side is along the positive horizontal axis. So you always start there, where it says red there. You always start there. And now it is measured counterclockwise from the positive horizontal axis to the angle measured as positive. Okay, Travis, what did I just read? I don't know what you're talking about. So if I have this, and I tell you that's 45 degrees, notice that I went counterclockwise. Now, you guys are all smart. I think you guys are pretty smart. If I do one complete revolution, so 0 degrees, if I do one complete revolution, how many degrees is that? Someone tell me.
360.
Yeah, 360. Good job. So since I have 4 quadrants, you can break these up into pieces of 90 degrees each. 90 there, and then 90 plus 90, that's 180 here. And then 180 plus 90, that's 270 right here on that part of the y-axis. And there it is. Now it does say, let's see, it is measured counterclockwise, so that means in the opposite direction of the way the clock goes. From positive horizontal axis, the angle measure is positive, and clockwise, from the positive horizontal axis, the angle measure is negative. So what does that mean? That means this, that if I have my grid there, and if I go down here like this, and I'm gonna say that's 30 degrees, this would be counted as negative 30 degrees. Cool or not cool, guys?
Cool.
Cool.
So cool.
Right. Yeah, very cool, I think. Don't worry, it's gonna get more exciting. I know you guys are like, oh my God, this is so awesome. This degree there, it has to be bigger than 90 because I'm in the quadrant 2. I'm gonna say that's like 120. And notice that I'm putting a little degree symbol in the upper right-hand corner for all of these. All right, then I ask a question. It says, all right, Cardinals, because you guys are Cardinals. 1 revolution is how many radians? Okay, well, 1 revolution, so I'm gonna draw a circle here. And you guys agree that 1 revolution on that circle is 360 degrees. I don't know why it's coming out really funny like this, guys. I guess maybe my tablet is old and I need a new one. So 1 revolution is 360 degrees. Well, what is it in radians? Well, circumference of a circle, the entire circumference is either pi d, or you might see it as 2 pi r. I'm gonna leave it as 2 pi r like that. Now, that's circumference of a circle. So if circumference of a circle engulfs the whole circle, then we can literally say that 1 revolution is equal to 2 pi. Notice I didn't put any units. The units is a radians. And actually, technically, you might see some physics books that says radians is a unitless angle. I guess I agree and I disagree. I mean, I agree. I know what they're talking about, but they use radians to dictate an angle, guys. And it's the same thing as degrees. The only difference is the word radians. And where does it come from? Well, if you wanted to know what 1 revolution covers, you would just multiply 2 times pi times whatever the radius is. So a radian is literally what is your radius. Did all that make sense? I'm gonna say it again. So if you wanna know like how much distance something covers. So if I had scissors and I were to cut it right here at that black line, and I were to lay this from end to end, so just start it end to end, this distance here would be 2 times pi times whatever my radius is. So that's why they say my revolution, 1 revolution is just 2 pi radians. And that's how you say it, just 2 pi radians. And it is an angle. So I know that it could be very easily, you can be confused very easily and say, but 2 pi times radius is a distance. And yeah, you're right. But if you just say this spins 2 pi radians, all that means is that it does 1 revolution. Does that make sense to everyone? I'm going to say it again, guys. If someone says this circle just spinned 2 pi radians, that meant that that circle went 1 revolution, because the circumference of a circle is 2 pi times radius. Does that make sense, guys?
Yes.
Maya Pena, did that make sense?
Yes, it makes sense.
Ms. Gonzalez, did that make sense? See, I'm starting to remember some of you guys now, so I'm going to start picking on you guys. All right, I'm going to pick on one more person. Ms. Aleman, did that make sense?
Yes.
All right, good. All right, so now that we said that, what else do we got to talk about? Okay, well, let's do this in radians. So I'm going to draw my grid. I'm going to put my grid in black here. And here's 0 radians. Notice that I didn't put any degree symbol. Here's pi over 2. And don't worry, if you've never seen this before, I'm going to tell you exactly where I'm getting this, where I'm getting those numbers from. 3 pi over 2, 2 pi. You just told me a little while ago, just like a few seconds, that you understood that 1 revolution meant 2 pi. That's what you guys told me just a little while ago. So 1 revolution is 2 pi radians. Okay, well, if I come here to the side, do you guys agree that if I just do this right here like that, that's 1/4 of a revolution? Do you guys agree that's 1/4 of a revolution?
Yes.
Yeah. And if I take 2 pi and I multiply it by 1/4, well, look, 2 goes into 4 twice, so you just get pi over 2. So pi over 2 is equivalent to, do I still have it over here? Pi over 2 is equivalent to 90 degrees. See? If I do this in red, if I go from here to here, that's half a revolution. Half a revolution. Well, if I take 2 pi and I multiply by half a revolution, you just get pi. So pi is equivalent to 180 degrees. It is equivalent to 90 degrees. Is this making sense, guys?
Yes.
Okay. Now, even if you didn't, like, it doesn't matter how you do it, the math is always going to be correct. So let's say you want to do it in pieces of pi over 2. Like, well, this in black here is pi over 2, and then this right here between this right here with that one line, that's another pi over 2, and that's another pi over 2, and that's another pi over 2. So I'm going to erase it, guys, because it's starting to just look nasty. So what I'm trying to say is, you could have always done this. You could have always said, what's pi over 2 plus pi over 2? Well, that's 2 pi over 2. And look, the 2's cancel out, and it's just pi. Well, yeah, you take half a pi, and you add another half a pi, and you're going to get a whole pi. Cool or not cool? Cool. All right,
Cool.
so I think, let's see, I think we're kind of ready. When am I going to decide whether we know what quadrant we're in? No, I think we're good. I feel like I did more detailed in first period than I did with this class. I hope I'm not missing anything. I guess the last thing here, if I go clockwise, so 0 radians, if I go clockwise, this would be a negative pi over 2. This would be a negative pi. This would be a negative 3 pi over 2. And then finally, I'm back at 2 pi. You're always going to start at the x-axis, the horizontal part of it. And if we have more questions, we'll come up here and talk about it. Okay, coterminal angles. Let's see what this says. 2 angles in standard position. Standard position just means like where you're located at, what position are you at or whatever, are coterminal if and only if their radian measures differ by a multiple of 2 pi. Okay, we'll talk about that. That is, phi and theta are coterminal if and only if phi equals theta plus minus 2 pi n, or n stands for any integer. Let me talk to you. Oh, by the way, that's phi. Sometimes they say phy. That's theta. The, I think it's theta, or the thetha. No, I think it's theta. I think it's like that. It might be ha. Check whenever you get a chance, do a Greek symbol search and put theta and see what pops up. They're just Greek letters, guys. They can use really any symbol for an angle. What does this mean? All right, let's start with degrees first because I think you guys are better with degrees because you guys have more experience with degrees. So this means this. So here's an angle in standard position. I'm going to call that 30 degrees. Maybe I should start it with radians. Yeah, let's start with radians. Sorry, guys. Look, they give me a formula in radians first. So let's start with a radian. I'm going to call that pi over 6, which is the same thing as 30 degrees, actually. All right. So where does this 2 pi n come from? Well, n just means any integer. In case you don't know what integer means, it means whole number. Any whole number. And really, the n is like how many revolutions you've done. Revolutions. Like how many? Because remember, you just told me a little while ago that 1 revolution is 2 pi radians. Right there. You just told me that. So that's why there's a 2 pi there. So if I go right here, if I start where that black line is, well, I guess they're all black at the moment. And if I go like, let me turn that black line into a green line. So there we go. Well, now my ray is green. If I take that red, if I rotate that that green line, or not rotate, but if I continue spinning about the origin, 360 degrees or 2 pi, this is theta right there in red, that's a 2 pi. And if you do that, you land exactly in the same location as the green arrow. See? So that's what you call coterminal, that they're all the same. Now, if I want to get what that angle in red is, like the official angle, I would go theta equals, or I guess phi, if I want to know what phi is, phi equals my theta, which is pi over 6, plus 2 pi. And let's see, common denominator, I need a 6 in the bottom, so that means that turns to a 12. 12 divided by 6 is 2 pi. 12 plus 1 is 13 pi. 13 pi over 6. And I know what you're thinking. You're thinking like, man, Chavez, you're making this really hard when it's actually really simple. Like I could have told you that this is 13 pi over 6 because you starting here at the horizontal axis, you do a whole revolution, which is 2 pi, and then you just add another pi over 6. And 2 pi is the same thing as 12 pi over 6, and you're just adding a 1 pi over 6 to it. So that's 13 pi over 6. Yes, I get it. Like, I'm not insulting your intelligence. I know that you got it, but I'm just trying to use this formula here. All right, ask me questions, guys, because I know there's someone out there that is looking at me and is probably whispering or talking in their head saying, I don't know what this guy's doing, and I have no idea what he's saying, and I am totally lost, and I don't even know if I want to continue. Okay, maybe you're not saying all that, but what's going on? Phi and theta are just symbols for angles. We could use any type of symbol. Sometimes they use beta, that stands for beta. Sometimes they use alpha, that stands for alpha. Let's see, what other symbols do we know? Those are the main ones, but they can use any symbol. Oh, I made that up. That's an example. I made the pi over 6. All right, give me some more questions, guys.
Could you explain why you added the pi, or like what you added and like why you did it?
Oh, well, they wanted to know what angles are in the same position. So if I told you to graph 13 pi over 6. If I told you to graph that, you would go, oh, okay. So 13 pi over 6 is the same thing as, let's see, I do a whole revolution, that's 2 pi, and then I do another pi over 6. So that right there is 13 pi over 6. Now, Chavez, how did I get that? Well, I did a whole revolution, which is 2 pi, and then I added another pi over 6. So what I'm trying to say is that pi over 6 and 13 pi over 6 are coterminal. Chavez, I don't know what you're doing. Coterminal means that
So
both rays are the same. Okay, someone asked.
So they're coterminal because they end up at the same point.
Yes, because I wouldn't call it a point. I would say they are coterminal because both rays are aiming in exactly the same direction.
Okay.
Okay, I see the chat box is lighting up. How did I get 6 and 12? 6 and 12 from what? I'm confused. Like the pi over 6, that was given. And then I'm adding 2 pi. Oh, okay, so I got you. I think I get you. So this right here is 2 pi. Let me circle it. And the only way I can add 2 pi to pi over 6 is to get a common denominator. So I turn 2 pi into 12 pi over 6. 6 goes into 12 2 times. So there it is. That's 2 pi. And then I just did 12 plus 1. So 13 pi over 6. Common denominator. Once the denominator is set, you can just add the numerators together. 12 pi plus 1 pi is 13 pi. Okay. Next question, guys. Are we good? Do we kind of get it?
I'm still a bit confused on like why are we doing 2 revolutions?
I didn't do 2 revolutions. I did 1. 2 pi is 1 revolution. See, I just did 1. If I did 1 revolution, I'm back at the same location. I could have done 2 revolutions. I would have added 4 pi. Maybe you'll get it better when I talk about degrees. So let's talk about degrees real quick. What if I have degrees? So if I have degrees, this formula, well, instead of saying 2 pi n, 2 pi times n, how many degrees are in a revolution? Uh-oh. How many degrees in a revolution, guys?
360.
Yeah, 360 degrees. So maybe you'll understand it better this way. So let me do the same graph, but this time in degrees. The question that I'm going to ask, so here's a ray in green, and this angle here is 30 degrees. The question that I'm going to ask is, give me another coterminal to 30 degrees. Well, if I want another one, I can just add 360 to this guy. That black line there, or that black revolution, that's a whole circle, as you can see there. So I just did another revolution. So all I did there, so let me put what I did. So all I did, and I guess I should change the symbol there, is P equals my 30 degrees initially, and I went another revolution, 360 n. Well, n is 1. So I did 30 plus 360. So 30 plus 360 was 390 degrees. So theta is 30 degrees and theta is 390 degrees are equivalent. They will create the same ray. So they are coterminal to each other. Does that make sense, Ms. Harris? Does this make sense, Ms. Cano?
Yeah, I like the degrees better than the other one.
Yeah,
The
everyone likes the degrees better than radians because you guys have been doing degrees since like 4th or 5th grade. Then you take a course called geometry, and everything you do in geometry, all of it, almost all of it, is in degrees. And you should have been introduced to radians in geometry, like somewhere along the way. But if they didn't, well, then that's fine. We'll just catch you up right here. So yeah, guys, if it's in degrees, it's this formula. And look, we just came up with it with logic. We didn't even really use, well, I guess I told it to you, but we could have figured it out with logic.
I have a
All right,
question.
go. Yes, ask.
So are you always going to have to add a revolution, or is that just for coterminal angles?
That's just for coterminal. If I want coterminal angles, you always have to either add or subtract a revolution. There is no other way that the ray will be in the same direction if I don't do a revolution from the ray, from the reference of the ray. Does that make sense?
Yes, thank you.
All right, a reference angle. This is super extremely important. The rest of your physics career and math career is going to be based on this. The reference angle is super extremely important because we are bipedal human beings and we are always referencing to something. So that's why reference angles are so important. And I know that I just said something so broad and so general, and you're like, Chavez, you didn't even give anything specific. Okay, relax. I'm going to help you out in a little bit. So it says here the reference angle of an angle in standard position is a positive, underline the word positive, acute angle between the horizontal axis and the terminal side. That just means where it terminates, right? Where ray terminates. Where it ends. Okay, so let's see if we understand this. Let me see how smart you guys are. So I'm gonna draw, and I'm gonna create a ray. I'm gonna start at the origin, just like the instructions say, and I'm gonna create this ray. And I'm gonna say, you know what, let me put it closer to the y-axis. I'm gonna say, bam. I'm gonna call this, I'm gonna call that, what do you guys like better, degrees? Degrees. I'm gonna call that 120 degrees. What is the reference angle? Well, according to this, it says that it's a positive acute angle between the horizontal axis. Well, here's the horizontal axis right here. All this in blue. And it needs to be an acute angle. So then that means there must be talking about this angle here. So that's my theta, and I put a little r to indicate that it's a reference angle. Now, because I know the distance from here, so look, this in black, I know that this distance is 180 degrees. I know that for a fact. So because I know that for a fact, my reference has to be 180 degrees minus 120 degrees. So my reference is 60 degrees. Do we have any questions on how we got that, guys? Is that a no?
Is the reference angle always based off of 180 degrees?
No, not always. What if I have, let's do another one. What if I have, if you lie in quadrant 2 or quadrant 3, it's going to be based off of 180. But if you lie in quadrant 4, what if I have this? So I got this angle. And I'm going to call that angle 340 degrees. I want to know what this angle is. That's my theta reference now. Well, if this is 340 degrees, one revolution, you're only 20 degrees away from one revolution. So there it is. This is my reference angle. So I'm going to go 360 degrees minus 340 degrees, and that's going to give us 20 degrees. So my theta r in this case is 20 degrees. See? I'm going to do another one. Relax. I'm going to do two more. So what if I'm right here at 210? 210 degrees. Make sure you put a little degree symbol in the upper right-hand corner. Well, the reference angle, it's always with respect to the horizontal. That one in red. Theta r. So I know that from here to here, well, I guess I should not use red anymore because I'm already using red over there. So I know this distance here is 180. So I'm going to go theta r equals 210 minus 180, 30 degrees. Let's do one more. Man, I wish I could speak French. I can do Pig Latin.
Francois.
Man, I'm jealous. I really am. I'm like, you think I'm kidding, but man, I wish I could speak like 5 or 6 languages, man. That would be so awesome. All right, this one right here. My theta is 35 degrees. Well, in this case, if you're, and this only applies if you're in quadrant 1, because you're already acute and you're already with the horizontal axis. So in this case, your reference angle is going to be 35 degrees. Is that making sense, guys?
So would it usually only be in reference to 180 or 360 then?
Yeah, never with the y-axis, always with the x. So either the 180 or the 360. Cool. Chavez, why do you only reference it with respect to the horizontal axis all the time? Oh, because we're human beings and or Homo sapiens or whatever you call us, and we walk on a horizon, on a flat surface. So anytime we make measurements on Earth or anywhere really for that matter, we're making the measurements with respect to the horizon, right? So yeah, so it's all really just based on your reference. So when you get to physics, you'll see what I'm talking about. Are you guys taking physics right now? You are, right? Yeah, so you'll see what's up. Have you guys already started doing something similar to this? No, like sine 45.
We're on kinematics right now.
Okay, so you will get close to this eventually. And when you get this, you're gonna be like, yeah, we did that in pre-cal. It's the same. That's because like math is just everywhere, right? Yeah, terminal side can be a y-axis. If I say theta is 90 degrees, boom, terminal side's right on the y-axis. All right, this says sketch angles, and I have all these angles in standard position. That just means how does it look in quadrant 1, 2, 3, 4? Where does it terminate? That's all it means. Where does ray terminate? And calculate the measure of each reference angle. All right, no big deal. I can do that. We can do that. 71 degrees. What quadrant am I in?
Second.
The first quadrant. It's okay, guys. We're all in this together, so it's all good. So in case you want to know the quadrants, label them. That's quadrant 1, quadrant 2, quadrant 3, quadrant 4. That is a common ACT question. They will ask something about sine and cosine. We're not there yet. We're going to get there later on this week, or actually next week, but we'll get there in time. If it helps, you can do this. You can label your axis 0 degrees, 90 degrees, 180 degrees, 270 degrees, comma, 360 degrees. So the positive x-axis is the 0 degrees and the 360 degrees. If that helps, do that. All right. Theta r. The reference is 71 degrees because you're already in quadrant 1. It's between 0 and 90 degrees. That makes sense? It's with respect to the horizon. Don't worry, we'll do some more and you'll see what's up. Guys, you guys okay over there?
Yes.
All right, I'm gonna label because we don't want anyone to get scared. 0 degrees, 90 degrees, 180 degrees, 270 degrees, comma, 360 degrees. There it is, I did my full revolution. 133, what quadrant is that gonna be at?
2.
Yeah, quadrant 2. Quadrant 133 is probably something like this. Does it have to be perfect? No. I'm going to say that's 133 degrees, put the degree symbol. So if that's 133, my reference angle, this is my reference angle right here, theta r. My reference angle is 180 minus 133.
80 minus 133. Okay.
And that gives me 47 degrees. We still doing okay, guys? Oh, I should have done some of these standard positions with radians, darn it. This is where it terminates. It terminates at 71 degrees. So you always start at the x-axis, horizontal, and then you go counterclockwise, 71, 71, stop. So I'll go slow, watch. Ready on this one? So I'm gonna label 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then finally one revolution, 360 degrees. Okay, so start on the positive horizontal axis. And then we're gonna go counterclockwise until I hit 254 degrees. And 254 degrees is gonna put me in what quadrant? Perfect. So here we go. I'm starting at my positive x-axis. Here's my positive x-axis. You always start there, guys. And I'm going 90, 180, and then all the way to 254. That's going to put me in quadrant 3. Somewhere like right there. There it is. That is 254 degrees. I need to know the reference. It's never with the y-axis. It's always with the x. The reference is this one right there in green, guys. How do I get it? Theta r equals, I take my 254 and I'm going to subtract 180. So when I do that, I get 74 degrees. Are we okay, guys?
Yes.
All right, here we go. Last one, 317. You always start on the positive x-axis. Here it is. That's 0 degrees if they ever ask. And I go to 317. I'm going to label my axis here, 0 degrees, 90 degrees, 180 degrees. Remember, you're starting at the origin and you're doing a sweeping motion from the origin, because you're like the spindle of a clock. You're just rotating. That's all you're doing. Okay, so you start on the positive x-axis, and I'm going to go to 317 degrees. That's going to be in what quadrant?
4.
4. So I go, here I am 90, 180, 270, and I don't know, somewhere like right there. And I know I didn't make a straight line there, but origin, something like that. So that angle there was 317 degrees. It doesn't have to be perfect. My reference angle is this one right here in blue. Well, I'm sorry, guys. I mean, it's blue to me, but if you're colorblind, you're not going to see that as blue. So I don't know what color you would see that if you were colorblind. So hopefully no one's colorblind. And to find that, you're going to just do theta r. Oh, well, let's keep it as whatever this color is. Theta r. Theta r. 360 degrees minus 317. And that's some number, 360 minus 317. And I got 43 degrees. And there it is. How do we feel? Do we feel okay, guys?
Pretty good.
All right, good. You should, because we're all smart and we're getting the best education we can. Ms. Harris, you feel okay? Just wherever it terminates, just stop. Ray, you know what I mean? All right, don't worry, we're gonna do some more. All right, here we go. Example 2, find an angle in each quadrant with a common reference angle with 204 degrees from 0 to 360. All right, before I even start, read it again. If you don't understand what it's asking, find an angle in each quadrant. So underline angle in each quadrant with a common reference angle. So underline common reference with 204. And then I would double underline the 204 from 0 to 360. So what does that mean? What does that mean, Chavez? Chavez, I don't like this. Chavez, I don't like you impersonating me, talking about what I'm thinking. All right, I apologize, guys. I'm sorry if I'm getting on your nerves. Trust me, that is not what I want to do here. 204 degrees. Before I even start, where is 204 located? Like what quadrant is 204 degrees located at? Yeah, quadrant 3. Does everyone agree that's in quadrant 3?
Yes.
Yes.
Yeah. All right. So, and then 360 over here again. So here we go. I'm going to go to quadrant 3 to 204 degrees. I'm going to say 204 is right there somewhere. That's 204 degrees. What they want this guy in green, theta r. They want to know what that reference angle is. So to find that, I'm going to go theta r equals, and I'm going to go 204 minus 180. So I take my little calculator, 204 minus 180, and I'm not insulting your intelligence. I know a lot of you guys can do that in your head. So I'll go theta r is 24 degrees, and there it is, and that's it. So I found this reference angle. Look what they're telling me. It says find an angle. They want an angle. Really, I should have put I should have put angles, but it says in each quadrant, so I guess it reads okay. So I think Ms. Grajeda would approve of this. Find an angle in each quadrant. So they want that 24 degrees as a reference angle in quadrant 1, in quadrant 2. In quadrant 3, I don't have to worry about it because I already have it, but I'm going to give it to them anyways, and quadrant 4. So here's how it looks in each quadrant. I'm going to draw all of them. 1, 2, 3, 4. All right, in quadrant 1, In quadrant 1, if I want the reference angle to be 24 degrees, it's going to look like this. Theta R is 24, and so is theta is 24 degrees. So in quadrant 1, so I'm going to label it right here somewhere. In quadrant 1, Q1, the angle that they want is 24 degrees. In quadrant 2, I'm going to say quadrant 2. What do they want? Theta equals, here's quadrant 2, and I got to show 24 degrees. This is the 24 degrees right here, guys. I tried to put 24 degrees there. The angle they want is this angle. How am I going to get it? 180 minus 24. That's 156. So this angle is 156. In quadrant 3, it was already given. It's this one. That's 24 degrees. And this distance from here to here, that's 204 degrees. So this was already given. Quadrant 3, 204 degrees. And in quadrant 4, it looks like this. This angle there, that's your reference, theta R. I'm going to call that 24 degrees. The angle they want is this one, theta. I go 360, and that's subtract 24, and you get 336. So in quadrant 4, theta equals 336 degrees. Excuse me. Is this making sense, miss?
Yes.
Yes.
Okay. Awesome, guys. Don't worry, I'm gonna make a video. I feel like I spoke more and I put more detail into first period video, because first period video was like an hour long, an hour, 10 minutes, and y'all's video is gonna be really short. I don't know. I'll look back and see what I did that I gave them more detail or what. All right, so there was one kid, I'm talking like a long time ago when I first started like teaching this. He made me laugh. He was a really funny guy. I'm not gonna say that he wasn't good at math, because he was all right. But I mean, I think anyone who's funny, okay, no, look, we don't base grades off of funniness, guys. We base grades off of what we know. No, that is the truth, because I want to be fair to everyone, period. Plus, I want to offer the best education. And please, guys, don't make this about a grade. Let's make sure that we make this about actually learning. So it says sketch an angle of 4897 degrees. And this kid, so the reason I'm bringing him up is because he made me laugh so hard with this question in particular. Maybe not this exact one, because I don't remember it, but it was something big. It was something big. And he actually did it correct. It was like, I don't know, 5,000 degrees or whatever. And he did this. He goes, okay, 360, 720. And he did a whole bunch. He did a whole bunch of these. Like, I don't remember how many, but a whole bunch. He filled it all up and he got it. And he's like, oh, it ends right there. And then he put his arrow. And as you can imagine, look, think about it. Like, it was a big number like this, and it was way more than that. And he made me laugh because I'm like, man, this kid, he's smart, obviously. He didn't have to do that. He obviously knew the concept, but you don't have to do all that. So don't make me laugh in a good way. I'm not saying that's laughing in a bad way, because he at least knew what he was talking about. Here's how you do this question. Don't do it like that. Don't do it like him. Do it like this. Take the 4897, because that's what they want. They just want an angle. They just want to know where it terminates. So I'm going to put, where did it terminate? Where does it, quote unquote, terminate? Take the 4897, and that's degrees. And in one revolution, how many degrees are there? Yeah. Divide that sucker by 360. So I take my 4897, I push division, and I go by 360. And you're going to get a really long number, here. 13.602777778. Do not delete that number. Keep it all in there, because we want to get the perfect answer. So hopefully you guys understand number theory. So that 13 there, the specific 13, that means that you did 13 complete revolutions. This means, quote unquote, you did 13 complete revolutions. All right. The 0.6027778, that in green, that means you did 0.6027778 revolutions. And I should just take out the S because it's a revolution, right? It's less than a revolution. So make sure that we're smart, guys. It works like the decimals work like that for everything. So yes, you're right. If you're thinking, I don't know if you're thinking this, maybe you're just completely lost and you have no idea what I'm talking about. That 0.6027778 is a percentage. That's a percentage of a revolution you did. If someone asks, what's the percentage of a revolution you did? You did 60.277778% of a revolution. Does that make sense, guys?
Yes.
Yes.
Okay. And it works the same way with everything, guys. If someone tells you it takes you 3.2 minutes, that means it took you 3 minutes and 20% of a minute. So how do I turn this 0.6027778 into a degree? Well, simple. You take this number, all of it, 0.6027778. Don't round, just keep that number in the calculator. So I'm just going to tell the calculator subtract 13 to give me that number unobstructed. And I'm going to multiply that number by how many degrees are in a revolution. And that's 360. So I'm going to go times 360. So times 360. And the calculator should, if you didn't do anything funky, the calculator should give you a perfect 217 degrees. If you did something funky, then it's going to give you 216.9999999 or 217.000001. But I didn't do anything funky, so it gave me a perfect 217. And now that I have 217 degrees, I know where this angle is at. That 217 degrees is in what quadrant?
Three.
Yeah, quadrant 3. Sorry, I'm just making it a habit to always put those labels there for you guys. So you're somewhere there. You don't have to be perfect, as long as you're in the right quadrant there. 217 degrees, there it is. They wanted me to find the reference angle. The 48, by the way, the 4897 and the 217, look, we have an opportunity to use the vocabulary words that we just did right now. Those are coterminal. Those are coterminal angles. They both share the same ray. Okay, now that we got that out of the way, let's get our reference angle. Our reference angle is this guy here in green. And I'll just take that 217 and I subtract from 180 and we get 37 degrees. So my reference angle is 37 degrees. So there it is. Maybe put it here somewhere on the side. Theta, this is called a theta, guys. That symbol there. This is called a theta. It's the most common one used for degrees. I mean for an angle. Not necessarily degrees. It could be radians. How do we feel so far? Are we pretty good, guys? Can we take some more? Can we do some more math? I mean, I can do math all day, but can you guys do some more math? Is that a yes?
Yes.
Okay. You guys scared me there. It says convert the following radians into degrees. So here we go. You already know, what do we know? Let's see. We know that 360 degrees is 1 revolution. And we know that 2 pi radians is also 1 revolution. I could use the 360 and 2 pi to make some type of scale, but there's an easier number than 360 and 2 pi. What's the easier number? Well, let's see, I have 2 pi. So how many degrees are in 1 pi? Yeah, 180. So I'm gonna go ahead and draw a little scale here, guys. See, this is 180 degrees, and this is also in radians, that would be pi. So I'm gonna use that fact. I'm gonna use the fact that 180 degrees equals pi radians. As long as you have units like that, those are the same. Notice that I put a degree symbol in the 180. 180 degrees equals pi radians. So what do? I take the pi over 3. This is a radian. Notice it doesn't have, like, you can write out the word radian if you want. And I'm going to multiply it by, what do I want? I want a degree. I'm going to multiply by 180 degree over pi radians. My radians are going to cancel out, and I'm going to be left with degrees. 3 goes into 18, 6 times, so that must be 60 degrees. Does everyone see what I did there, guys?
Yes.
Okay, and that's all I'm going to do, guys, over and over again. Look at this. 2 pi over 3. I'm trying to convert that radian to degrees. So I use my scale factor, or my, not, this is not, technically it's not called a scale factor. I use my little conversion. 180 degrees and pi radians. Pi's cancel out. Let's see if we can do this again. 3 goes into 18 6 times. 6 times 2 is 12. So this is 120 degrees. Let's keep going. 4 pi over 3. I'm going to multiply that by 180 degrees over pi. 3 goes into 18 6 times. 6 times 4. 6, 12, 24. So 240 degrees. You can use a calculator if you want. 5 pi over 3 times 180 degrees over pi. Make sure to put the degree symbol there, guys. Pi's cancel out. 3 goes into 18 6 times. 5 times 6 is 30. So this is 300 degrees. Excuse me. And then last but not least, 11 pi over 6 times 180 degree over pi. The pi's cancel out. 6 goes into 18 3 times. 11, 330. 330 degrees. Someone in first period said, can I just replace pi with 180, like immediately? Yeah, that's fine. You can do that, but it won't always work. But yeah, you can do that. I am. I'm doing 180 times 5 and whatever that is divided by 3. Or you can do 180 times 5/3 and you'll get the 300. I just did it like mentally. So I go 3 goes into 18 and then whatever. What was the question? Someone had a question, guys?
I was going to ask if it would be the same if you did it the opposite way when converting to radians.
Yes. If you're going from degrees to radians and they give you degrees, it would be the same, but instead of 180 degree divided by pi, you're going to multiply it by what? Oh. Hello, miss. Are you still there?
Pi.
If you're going from degrees to radians, you have to switch your scale here, or not the scale. Your little, instead of 180 degrees by pi, you have to go pi over 180.
Okay.
You know what I mean?
Yes.
Okay. Now check this out, guys. Some students think that the level 1 SAT math subject exam is really hard. It's not. It says, this one says, what if my radian does not have a pi in it? And notice this is from the level 1 math SAT. It says convert the angle 2.5 radians to degrees, rounding to the nearest tenth. Okay, notice there's no degree symbol or anything, so that's definitely a radian. So that's how you differentiate between radians and degrees, that little upper right-hand corner there. So you take your 2.5, that's a radian, and 1 degrees, so I'm gonna multiply this by 180 degrees over pi. And now you're gonna be forced, the pi's not gonna cancel, you're gonna be forced to multiply, right? So 2.5 times 180 divided by pi. And I have my little calculator here on the side, guys, so you guys can't see it, but I get 143.2394488 degrees. They want it to the nearest tenth, so 143.2 degrees. If you don't put a degree symbol, if I tell you to let's say I told you to give me 217 degrees or give me the reference angle, and you don't put the degree symbol, like if you don't put this guy, if you don't put that degree symbol there, it's gonna be wrong, guys. Because if you tell me some angle and you just write 37, that means it's a radian, not a degree. So make sure we know the difference. You know what I mean? Because if I tell you 3.14 radians, well, everyone recognizes that as pi radians. So 3.14 radians is almost the same as 180 degrees because 3.14 is rounded, right? And then pi itself goes on forever, 3.1415 to blah, 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 whatever, for those that haven't memorized. All right. Now we get to example 5, and we're still sketching angles, but now they're in radians, your favorite. That was a joke, but I realized that it wasn't funny, so I'm sorry, guys. I'm telling you, time would pass by so much faster if we all had like cats and puppies like with us. We could be petting our pet puppy while doing math. Man, that'd be pretty awesome, I think. That sounds like a pretty good life. All right, so it says sketch angles of pi over 3. All right, let's see how smart you guys are. Where is pi over 3? Quadrant 1, 2, 3, or 4? I don't know, Chavez, you tell me. Yeah. Here's how you do it, guys. Let me help you guys out. You can think of pi over 2 as half of pi. You can think of 3 halves of pi, or 3 pi over 2 as 3 halves of pi. In case you don't know what 3 over 2 is, it's like 1.5. So you can think of that as 1.5 pi. It's not, writing 1.5 pi is not wrong, guys, but writing a decimal with something that goes on forever like that just looks funky, and it's frowned upon in the math world. So yeah, so that's why, don't be doing that. But I mean, I guess you can if you want to, if you want to give your professors a hard time over there. All right, pi over 3. Think of that as saying 1/3 of pi. Well, 1/3 of pi is 1/3 smaller than a half, or is 1/3 bigger than a half?
Smaller.
It's smaller, so it must be in quadrant 1. So it must look like this. So this angle there must be pi over 3, see? And then it wants me to measure the reference angle. Well, if I'm in quadrant 1, hopefully by now you probably already got it. The reference angle is gonna be the same thing, only if you're in quadrant 1. Because it's definitely a acute angle already. An acute angle, not a cute angle. Because, what's a cute angle anyways? Like, is the angle like cuter? Like, is there a little, like, oh, look, that's a cuter angle? Like, no, like, come on, guys. We don't play those games here. This is math. I gotta have some fun. I apologize, guys. All right, 2/3 pi. Is 2/3 pi bigger than half a pi? I know you know, but I'm waiting for these guys. Is 2/3 pi bigger than half a pi, guys?
Yes.
Yeah. Is it bigger than a whole pi?
No.
No. So I'm going to be in quadrant 2. So here it is. It doesn't have to be perfect. You don't have to draw it perfect, guys. Here is 2 pi over 3. Theta equals 2 pi over 3. The reference angle, that has to be pi over 3. Chavez, how did you get that so fast? I know, here's how I got it so fast, guys. I know that this distance here is pi. I know that. Well, 2 pi over 3, if I add 1/3 of a pi, it's going to complete a full pi. Do you guys see that? If you guys don't see that, then you're just going to have to do it like this every time, which I guess, it might slow you down a little bit, but you'll still get it right. So if you don't see that, you can do this. My theta reference equals the distance from here to here. We just said that was pi. So you can say pi minus 2 pi over 3. And then we just get a common denominator. So 3 and 3, see? 3 over 3 is just 1 pi. And then 3 minus 2 is a single pi. Keep the 3. See, guys, it's all beautiful. All of it is beautiful. 4/3 pi. 4/3 pi, 4 over 3, in case you need to know what this is in decimal. 4 over 3. 3 goes into 4 one time, and then I have 1 left over, so it's 1 1/3. So it's like saying 1.333 goes on forever with a pi on it. Well, this is 1.5 pi at 270 degrees. So 4 pi over 3 has to be in quadrant 3. Is that making sense to you guys? Is that making sense, Ms. Harris?
Yes.
So now that I know that, and by now you can probably already guess the 4 pi over 3, you're saying like, well, you know, 4 is just one number bigger than 3. So that reference angle probably is pi over 3. And yeah, you're right. You're thinking correctly. If you're not thinking like that, relax. I'm going to help you. I'm going to write it right here. The theta r, oh, I guess I should keep it with the same color, right? For good notes. Theta r equals 4 pi over 3. And I'm going to subtract pi. So this in green is just me finding a common denominator, 3. And then 4 pi minus 3 pi, that's just 1 pi. And look, you still get pi over 3. It doesn't matter how you cut it, guys. Let's do another one. Another one. DJ Khaled used to say that all the time. You guys have probably never heard of him because you guys are pretty young. But he used to be a famous rapper. He might still be around, but he's not as famous as he used to be. 5 pi over 3. So let's see. That guy is like saying 5 over 3. 3 goes into 5 one time, and you're going to have 2 left over. So that's like saying 1 2/3. So that's 1.666. Oh, that's a bad number. I don't want to see that. 1.66 goes on forever with a pi on it. I want to go to heaven, guys. So let's stay away from evil. Not that, you know, it's just a number, so I don't think it really means anything. But anyways, 1.66 pi. So we already set that to 1.5 pi. So obviously it's bigger than 1.5, but it's not quite as big as 2 pi. So that's going to be in quadrant 4. So I'm going to be somewhere like right here. And that is that. And we're going to call that 5 pi over 3. And as you can imagine, by now you guys are already getting the hang of it. See right there, that would complete the whole circle there. So that would be pi over 3. Why? Because 5 pi over 3 plus pi over 3 is 6 pi over 3, and 3 goes into 6 twice. So there will be my whole revolution. So there it is. My reference, oh, I got to put an R there. My reference angle is pi over 3. And then last but not least, 11 pi over 6. Look how close that is to 2 pi. Super close to 2 pi. Chavez, how do you know? Well, if I added one more to that 11, that would be 12 pi over 6. And 12 pi over 6 is 2 pi. So it's only 1/6 of pi away, 1/6 pi away. So when you draw this one, now I'm not looking for perfection, guys. I'm not looking for perfection. But when you draw that one, I would like to see that it's noticeably closer to the x-axis than the y-axis. So I would like to see something like that. If you don't draw that, it's okay. I'm not going to take away points. As long as you give me the right quadrant, we won't take away any points. So that's 11 pi over 6. And you're literally just pi over 6 away, so 1/6 of pi. So that's your reference right there, pi over 6. You're pi over 6 away from completing 2 pi, guys. 11 pi over 6 plus pi over 6 is 2 pi. So there it is. Are we starting to get the hang of it, guys? Is that a yes? Is that a no? Is that a
Yes.
maybe? Okay. I hope I'm not putting you guys to sleep. I mean, I don't know. Math kind of wakes me up a little bit, but I don't know if it wakes you guys up. So now I have these. All I'm doing now is just converting to radians. So this is for that question. I think you had it, Penna. How do I convert degrees to radians? Well, here we go. We got a whole bunch. We have a whole bunch of degrees. We're going to convert them to radians. So I have 495. I'm going to write 495, put a degree symbol. And since I want to cancel out degrees, I have to put the degree in the bottom. 180 degrees in the bottom, put a pi on the top. And then I just go ahead and multiply this out. I leave it in terms of pi. So if you have a TI Inspire CAS, it will tell it to you in terms of pi. If you do not have a CAS, just do 495 divided by 180 and then turn it into a fraction. 495 divided by 180, and then that's 2.75. Don't leave it at 2.75 pi. Turn it into a fraction. So this is 11 pi over 4. All of these are going to have a pi in it, guys. 720, you probably don't need a calculator for this one. You recognize 720. 720, well, I think you guys recognize it because you guys watch skateboarding maybe. How many revolutions is 720? Yeah, it's 2 revolutions. So in radians, that is 4 pi. But if you don't see that, relax. I got you. I got you. If you don't see that, I got you. Look. 18 goes into 72 4 times, 4 pi. It makes sense. 2 pi is 1 radian. I'm sorry. 2 pi is 1 revolution. So 2 revolutions must be 4 pi. 60 degrees. Multiply that by pi over 180. 6 goes into 18 3 times. So this must be pi over 3. Okay. 165. Multiply this by pi over 180. You guys get the gist. Too simple. And now that it's getting back to simple, you're probably getting tired because anytime something is like really simple, you kind of lose focus because you're like, oh, I got it. It's too simple. That's only pi over 12 away from being a full pi there. See, 165 is pretty close to 180, relatively, I guess. 195 times pi over 180. So this is going to be slightly bigger than 180. So the numerator is going to be bigger than the denominator. Not by much, though. 195 divided by 180. Math, fraction, enter. This one's 13 pi over 12. See? And then last, but definitely not least, pi over 180. 12 over 18, is that 3/4 or something? 120 divided by 180. Math, fraction, enter. 2/3. 2 pi over 3. Oh yeah. 6 goes into 12 twice. 6 goes into 18 3 times. Oh man, I don't know why it didn't take me that long.